The broadcast is now starting. All attendees are in listen-only mode.
Well, good afternoon, good morning, good evening, wherever you are in different parts of the world. We are once again here with our IFEES, GDC, and IUC Global Webinar Series. We will take just another minute before we get started. My clock shows 6:29, which will go to 6:30 in just a little while. Just a second, I guess. So our speaker for today is Dr. Manel Martinez Ramon, and co-author for this is Ramiro Jordan. They're both from the Department of Electrical and Computer Engineering at the University of New Mexico. And as you can see, they are experts in machine learning. So, which is the topic of the day, and everybody in the world is excited about this topic. And I can see that we will soon have more than 200 people participating here today. So thank you all for joining this very contemporary webinar. So over to you, Manel. It's go ahead.
Thank you. So good morning, everyone. It's an honor for me to be presenting today this talk about machine learning. Yes, it's a hot topic. Everyone is interested in machine learning these days. And so I'm going to just give a little presentation that introduces these techniques. Machine learning is a well-established multidisciplinary area of research tackled from different points of view that include functional analysis, optimization, modern probability statistics, computer science and engineering, and also from psychology and social sciences. Machine learning has been defined in multiple clever ways, but I just like to say that machine learning is the set of technologies that allow us to teach machines how to take decisions by learning exclusively from the available data. And this is very important. The quantity, quality, structure, and information of this data is obviously a fundamental matter, as well as the nature of the problem that we want to solve in order to choose the structure, criteria, and algorithms to construct our learning machine. We are going to talk fundamentally about the structure of learning machines, not so much about algorithms or criteria for training them. One can think of machine learning as a way to process the data in order to extract the information conveyed on it, and then use this information to infer the knowledge that lies behind this information. We will see an example right now. But first, let me show you a rough, rather incomplete view of machine learning from the point of view of the data. So for example, let's assume that we have a bunch of data, for example, pictures of faces, and we have subjects of many ethnicities, cultures, all genders and ages, and we want to teach a machine to recognize the emotions of the people in the machine, the people that is seen by the machine. A typical setup would be to take a bunch of people to label each image with one or more of the 7 fundamental emotions. And if we can get a decent number of labeled images, we simply set up a machine to learn to classify these images with the labels provided as part of the information. And then we can take a picture of another face and use the machine to tell us what is the person's emotion. This is supervised learning, and we train a machine to do this by presenting the images at the input and computed the error between the desired and obtained output. Then the parameters of the machine are modified in order to reduce this error. The learning machine, what we have here, is nothing but a mathematical function with many variables. And this function can be represented as a structure with nodes, and often it's similar to the schematic representation of a small biological neural network. We will see some of these structures. But also, it might be the case that the data is just taken from the internet, right? For example, we have a bunch of faces from the internet, and we have 1 million faces, and no resources to label them. But we can still use a machine to extract the structure of the data distribution. And for this particular case, group or cluster the faces in groups that will hopefully represent different emotions. That would be non-supervised learning. In order to have an intuitive idea of what we want to, of what a learning machine can be, and in particular to distinguish between deep learning and shallow learning, we can imagine this following problem. We have a barn door that we use for that this is used for cows by cows and horses, right? So, and every time an animal crosses it, we want to determine whether it is a horse or a cow. I know it's a silly problem. It's just an example. And so every time an animal crosses, we take a picture. The machine is constructed under a hypothesis, and it is that I can distinguish the species just by measuring the height and the weight of the animal. Horses are taller and skinnier, and cows are usually smaller and thicker. You can argue that I have never seen a horse and a cow together, but that's okay. We take the pics, which are the data, and then a computer program takes the measures, height and weight. That would be the information. We do it many times, and we make sure that a human takes note of the species of each animal. And then when we have a lot of data, we can construct this graphic, this one. We assume now that my hypothesis is true. Then we take one sample, and it can be thrown in a two-dimensional space, as in the figure, where the features are represented as vectors. And then we go adding samples. That's another one. That will correspond to a cow, and that will correspond to a horse. Then the landscape will be as in the figure. You can see a data structure and a separation between cows and horses in a space in 2 dimensions. And these kind of structures in the data is what we want to be learned from the machine. The idea in this particular problem is to establish a separating hyperplane or separating line, in this case, within both classes. Mathematically, the line consists of all points that satisfy that the linear equation of these points is 0. Points at both sides of the line will have either a positive or negative response, and the sign will give me the classification. Following this idea, I can construct a machine with the aspect of this figure, where in each one of the nodes, we put each one of the training samples, and the nodes compute a similarity operation with the input sample. The similarity operation, which is nothing but a dot product of the input data with all the training data, is then multiplied by a scalar, alpha, and added together. This defines a separating line, or plane, or hyperplane if we have more than 3 dimensions in our space. So this is our previous machine. This machine is trained in a way that the scalars alpha are chosen, so the response of the machine is positive or negative depending on the class, or depending on the site in which the data is. The dot product can be changed by certain nonlinear similarity functions that are called kernels, right? We can change the dot products by other functions that have the same function, but they are not linear. And this is a very popular type of machines that are called kernel machines. Some of them are the super vector machines or the Gaussian process machines, whose difference is only in their respective optimization criteria that lead to different algorithms. These are 2 academic examples in 2 dimensions that demonstrate how such simple structures are able to solve problems that are nonlinear in nature. This is the typical XOR problem, and this is the double spiral problem. They have low complexity, these machines. They are easy to train, and they are useful when we do not have too many data available. But the low complexity does not allow them to perform high complex tasks. If we use too many data, then they are structurally too heavy to be trained, as the training has to be performed with all the training data at the same time, and the matrices that need to be manipulated increase with the square of the data. But if we don't have too many data, this is often the best approach. There are many applications of kernel learning where we do not have tons of daily data available, and where the problem to solve is not particularly complex, but still very challenging. One of the applications where my group and many others are working is in smart grid. We want to provide the electrical grid with intelligence for many reasons. The one that I am interested in is the case of grids or microgrids or nanogrids that have capabilities for low-scale solar energy generation and also energy storage in batteries. In grids with a high penetration of green energies, not only the energy usage, but also the generation becomes stochastic, which means it becomes random in nature. And we need to predict how much energy will be available and how much energy will be needed in order to optimize the non-deterministic resources dictated mainly by the solar intensity. In this example, we want to know how much energy will be needed for the next 24 hours. And we have two examples here. This is a relatively easy task if we have available historic energy load and weather conditions, as well as the weather prediction for the next day. But this prediction, the just simple prediction, can be improved in some ways. First, we can produce more accurate predictions if we are able to select the data to train by discarding the data that doesn't have information for the next day. For example, if we are in summer, last winter will not provide any information. Also, we want to predict the predictors to be able to characterize the power usage in order to interpret it. And also, as seen in these graphs, utility companies and other stakeholders will benefit of predictions that are provided with some confidence interval, so they can decide whether the forecast is reliable or not. And all this, it can be done using kernel-based learning machines and learning criteria based on probability theory. These are two examples of probabilistic learning kernel machines that accurately provide not only a mean value of the forecast for next day, but also a confidence interval. In this case, this is one method. This is another one. Which is working slightly better. On the other side, we have the very popular deep learning structures. The deep learning is based in the concept of neuron, which is a linear operation over all the elements of an input. I know that this is not exactly a real neuron, which is something way more complicated, but from a structural point of view, both are similar with axons and dendrites in a body. So the input is represented here by these small circles, and each element of the input is multiplied times a scalar, in this case wi. This operation, after this operation, the results are added together and then pass through a nonlinear monotonic function similar to the one that we have here in the figure. This is hyperbolic tangent. We can have a sigmoid, we can have other functions, and but all of them, they are monotonic. And the output is what we call the activation of the neuron. So we can construct a machine with many neurons, also called perceptrons, and the input and output layers are connected through two-dimensional tensors, which is they are connected through matrices of parameters. We can put together many layers, and the complexity of the structures, of this kind of structures, is often much higher than in the case of kernel learning. So they have many more parameters compared to the kernel learning, in which we have one parameter per training sample only. But these parameters, they do not depend on the number of data. The matrices that we are using in training here for the training of these machines, they have fixed dimensions, and the training can be performed one sample at a time, not with all the all the samples at the same time. So we can use as much data as we want, and we won't saturate the memory capabilities of our processor. This is the classical multi-layer perceptron or neural network, and the operation is can be done in parallel. These structures often they have thousands or even millions of parameters. The huge complexity and need often high quantities of data to be trained, but the tasks that they perform can be very complex if we are successful training them. For example, we can detect emotions, but we will see more examples later. This is an example, an academic example that I used with my students, and the input, it has 2 dimensions, and these 2 colors they are the classes that we have to separate, to classify. We can see here that the problem is easily solved with this structure. Of course, this is not optimal from a Bayesian point of view, but it's an example that shows how easily we can add complexity to this using these structures. So if we want to process images, we can construct our neural network using more sophisticated structure. So the inputs, it's themselves, they are matrices. So we can represent the layers in matrices. So the idea here is that we construct the neural network where the input is the image itself. It's represented as a matrix, as I said, and we let the machine extract the features by itself in constitutive layers. And all these cubes are fully interconnected. The aspect of the neural network would be like that. And the difference here between this and the previous one is that since we want to connect a matrix of features to another matrix of features, the connection parameters must be 4-dimensional tensors. But this is okay because we exactly know how to operate with them, just as with matrices. In order to train a neural network, we use the very well-known backpropagation algorithm. And roughly speaking, for each training sample, we compute the error between the obtained output and the desired one. And we transform the error back to the input by using the weight tensors. And then we modify using a gradient algorithm these tensors in order to reduce the errors. This is overly simplified, but here I just want you to have an idea of the mechanism, and the interested practitioner can find all the details in textbooks. And this is very well known. In more sophisticated structures that follow the idea of the multi-layer perceptron include the very widely used convolutional neural network. This kind of machine is particularly useful in image processing, for example, to detect and classify objects in images. The convolution in a neural network consists of a set of matrices, like these ones, whose values are convolved with the image. So we pass these matrices against the image. In the figure, the blue convolution kernel or matrix is passed through all the images to generate the first filter image. And the pink one generates the second image, and so on. And another kernel will generate the image number 3. Each convolution matrix produces a version of the image that is intended to be a higher abstraction feature extraction. For example, a convolution with a given kernel can extract the edges in a given direction of the image. But usually, the parameters that we put here inside, they are also trained using backpropagation as in standard neural network. As we will see now, the structural complexity of this structure is very high. There's a lot of connections here, but since the parameters are in the convolution kernels, its number, the number of parameters in the convolutional part of a neural network is low. Usually, we use several layers of convolutions, and which make features relatively invariant to rotations, translations, and others. So if we have an object in the image, the different convolutions will make the features of the object independent on the position or the rotation of the object. The outputs of the convolutions are applied to a nonlinear function and then fed into what is called a dense network. Here, what we do is to subsample this image, pass it through a nonlinear function, and this is passed to a standard neural network. This part of the process uses the features extracted by the convolution in order to proceed with the classification or other estimation tasks. The convolutional neural network was introduced in the 80s by Jan LeCun and co-workers as a structure specifically constructed to identify handwritten digits for the US Postal Service. The structure that we see here is called LeNet5. And here we see the same structure as before, but with the matrices in a different position. As I said, well, authors presented other less complex structures and compared them in performance. This one had a total of 340,000 connection parameters and about 60,000 free parameters. The input images were 20 times 20 pixel images with handwritten digits, and the error rate was an astonishing 0.9%. Later, kernel machines produced a classification error about 1.1 with a computational burden considerably lower, but this structure was the first of a class of learning machines that have numbers that have been applied to many problems with outstanding unbeaten results. This is why I believe that we can take a closer look at what this does. The first layer, which is labeled as C1, is the result of the convolution of the image with 5 times 5 matrices, and there are 6 of them. The number of connections is well over 100,000, but it has only 156 parameters. In layer S2, the previous image is subsampled in squares of 4 pixels that are added together and multiplied times a coefficient. This is a simple operation. The outputs are passed to a nonlinear function as in a standard neural network to produce 6 feature maps of 14 times 14 pixels. And this layer has a total of 12 parameters, but also 6,000 connections. Then we repeat the process in C3, which has the same function as C1 with different dimensionalities. And then this S4 has the same function as S2, but again with different dimensionalities. The outputs are vectorized and passed through a standard neural network. During the training, the desired outputs are coded such that the output corresponding to the label of the input is 1, and the rest are 0. There are 10 outputs here. So first output must be 1 if we have a digit 1. Second output must be 1 if we have a digit 2, and so on until last output, output 10, must be 1 if a digit and input is 0. And during the test, the decision about what digit is at the input is taken by selecting the highest of the outputs. In summary, a convolutional neural network includes one or more layers that perform a convolution operation, which is a linear filtering operation that produces several filtered versions of the image. This operation is performed several times, and it extracts higher level of abstraction features of the image. These features are then introduced in a multi-layer perceptron. This is an example of what the machine does. The input, a handwritten 0, is introduced into the 6 convolutions to produce the 6 images. The 6 images here. They are subsampled, passed through a nonlinear function, and convolved again to produce these tiny images here. The process is again repeated in this version of the LeNet, and then passed through a neural network that does the classification. In this case, it's a 0, and the answer is 0. But let's see the demonstration moving in the web page of Jan LeCun. In the center, you see the images that are fed to the input of the neural network, and in the left, you see the different levels of features extracted with the convolutions. The upper part shows the classification of this rather classic example that I extracted. What we are seeing is Jan LeCun's web page. The applications of this kind of technologies are infinite. And there are many convolutional neural network structures that are evolutions of the original CNN, and they are able to perform classification, regression, and other tasks as pattern reconstruction, which have been applied to images. In this example, we are presenting a structure which is a lot more cumbersome. And my team and I use deep learning to construct this structure, to construct a system which is able to take advantage of the data generated by a team of first responders on duty from their microphones and thermal cameras. And later we extended it to other sensors. Here we see a convolutional neural network that is combined with another kind of network, which is a region proposal network. And this later network detects regions of the potential interest in the images that contain firefighters or objects of interest. The so-called faster RCNN can classify the different objects in the scene with a probability of error below 5%. There is also a regression neural network that computes the coordinates of bounding boxes for the objects of interest, which allows a fast tracking of the evolution of the objects in the scene. Finally, we added a so-called mask RCNN, which produces masks of the objects in order to color them in the image for improved perception. All of them, they are evolutions of the standard CNN that we saw before. And what we did here is just to connect them together. You can see the details of this in this paper, and also I refer you to the original references of all these networks in order to fully understand the way in which they work. The infrastructure that we propose consists of a couple of cameras. One captures thermal images, and another one that is able to compute the depths of the images in order to produce 3D representation of the scene. This data is fed into a small GPU that can be carried in the figure in the 5-arcade gear. That's a small processor, and that processes the images with the neural network that we have seen before. The results they are transmitted through a communication system proposed by my team, and then presented it to the command of the operation and also to the 5-arcade through HoloLens in order to produce an augmented reality scene. Here we have some of the results of our system. Recall that in a fight round, the firefighter might be in a scenario where the visible light is not available due to the fire smoke and the emergency situation. At present, they have to relay in what they can see through a thermal camera. And here we see that the neural network is able to classify the objects in the scene, firefighters, doors, windows, and others, fire, and they produce segmented images that improve the scene understanding and understandability. Here we see several firefighters in different colors. Here we see a fighter in a window. Here we have a window, and there's doors in the other parts of the scene. Also, we use machine learning structures that can provide written or spoken descriptions of the scene. In these cases, the machine would say, there are 3 firefighters in a window, or there is a firefighter in the window and 2 standing. The machine is also able to determine whether the firefighter is standing, lying, or crawling, or whether there is fire in the scene. And all this with a very low probability of error. And we did everything with standard 4 kinds of standard CNNs. We also propose machine learning structures that are able to detect and characterize accurately, in an accurate way, fire and smoke in a scene. And this is done in real time, producing 10 segmentations of fire and smoke per second. Here we have background, smoke, and fire in 2 different scenarios. And we have high accuracy detection of fires with an accuracy above 90%. And this can be later used to determine how serious is the situation seen by the thermal camera. Another important approach based on the neural network structure is the autoencoder. This machine is based on the so-called restricted Boltzmann machine introduced by Hinton. It can be thought as the Boltzmann machine can be thought as a layer of a neural network. It's just treated differently, which leads to a non-supervised training. We can stack several of these, as in the first part of this diagram, with decreasing dimension, and the network can be trained so the figure, so the last layer of the figure keeps the probabilistic properties of the input data in a reduced dimension. The second part of the network is trained so it can reconstruct the input pattern. And the implication of this is that all the information of the data is preserved in this reduced dimension space in the center of the network. The convolutional autoencoders add convolutions at the input and the output, and in order to compress the information further and be able to process images. An interesting application of this consists of introducing images with missing areas and minimizing the reconstruction error with the original images. Then new images can be recovered from missing parts. Image processing using deep learning has produced outstanding results, for example, in hyper-resolution or in image in painting. And autoencoders is one of the techniques used in these tasks. Image in painting consists of reproducing credible image recovery in parts where the original image is lost. This is done by context encoders who use the surroundings of the image to interpret the missing parts and producing a synthetic substitute. This is done with autoencoders, as we saw before. This is constructed. The reconstructions are false. The same can be said about the machines that improve the resolution of images. If an image is an image of lost region, it's lost forever. But we can train machines with low and high resolution or complete and with intentionally missing areas in a way that if the machine is fed with a similar one, it can use the learned features to artificially reconstruct the image. As we can see here, all this, they are artificially reconstructed images using an autoencoder. In this application, we listen to the respiration of the firefighters on duty in order to estimate their breath, rate, and duration. This is something that we do in order to provide a machine with features able to determine whether a firefighter must get out of the scene to prevent accidents or strokes. So what we do is to take a short recording from the microphone of the firefighters, including their scuba masks. We extract some easy statistical measures, and we input them into the machine, into the first part of an autoencoder. And this autoencoder is able to fully automatically cluster different kinds of noises, in particular the respiration. Thus, the machine is able to separate the respiration noise from other noises coming from the scene by itself, thus producing a breath measurement that is robust with respect to the heavy interferences of the fireground. This graph shows, sorry about that, this graph shows measurements that have been compared later to the manual count of respiration rate and duration by a human, and the machine is able to do it with high success. We can use these autoencoders in a different way. We train the autoencoder to recover features extracted from data, and then essentially we discard the decoder part. This is what we did here. Another application for responders can be to detect the emotions of the people in the scene. In this work, we detect the 7 fundamental emotions using a simple neural network, using the first part of the autoencoder, actually. And in this work, we detect the 7 fundamental emotions using a simple neural network like that, which is trained in a semi-supervised way, and whose inputs are the features extracted from their eyes and mouths. This makes the detection very fast. We can detect in 0.02 seconds with a probability of error typically less than 5%. And we compare the probability of error of this deep learning structure to one supervector machine, which is kernel learning. And we see that deep structures there are much better for these tasks. To conclude this talk, we can say that machine learning is a prominent area, well established, very mature, and that allows us to use machines to take decisions only from the knowledge that they extract from the data. There are many areas of applications of machine learning, and they continue increasing as they are found as adequate data processing tools in many fields. The same can be said of machine learning research. I have heard many times that machine learning is closed, but this is absolutely not true. We keep doing research, and so far, many important theoretical and technological findings in machine learning research lead to new questions, still to be answered. And besides, we have seen here in this talk only a part of the broad spectrum of machine learning. I refer to the interested reader, attendant, to topics as, for example, recurrent neural networks, ensemble learning, reinforcement learning, self-supervised learning, and others. The future of machine learning is still going on to provide surprisingly outstanding results, and it will dramatically depend on the available computational resources and hardware still under constant evolution. Machine learning research and many resources as libraries and many databases are available for the public. It is done for the humankind to use it. Therefore, artificial intelligence in general and machine learning in particular are key technologies for peace engineering. This concludes my talk. Thank you very much for your patience, and I'm opening to questions.
Okay, wonderful. Thank you so much, Dr. Manel. We have with us actually Dr. Ramiro Jordan also has joined. Maybe he might want to say a few words. Come in, Ramiro. Oops, I'm trying to unmute you. Let's see. You can unmute yourself, I think. Yeah, go ahead.
Thank you, Krishna. Thank you, Manel. Excellent presentation. I know it's a very complicated subject, but I think you just gave the essence, and it was very clear. This is a research area that we're using in what is known as peace engineering, especially with emotions, detecting how people feel. So it's an open area for research, and we're looking for collaborations. So I want to thank you, Manel, again. Thank you, Krishnas, for this opportunity, and we're ready to engage in collaborations. Thank you.
Okay, let's see. We have any comments or questions from the audience? Come on in, everybody. We have time for plenty of questions, actually. So let's come on down. Okay. Let's send them in, and we'll talk about them. We'll get a chance to get your questions answered. Okay. So most of the cases, machine learning and deep learning, are they mainly with image processing? That's a question. Manel, for
yes. you? Yes. Well, not quite. There is a lot of images out there. Most of the information, or a lot of the information that we have, come from images, and there is a lot of applications that they are tied to images. And actually, this CNN that I presented was primarily used in images, but there are a lot more applications of CNNs and other kinds of deep learning. For example, we can apply it to communications. One of the lines of research of my group is in communications, and we apply both kernel learning and deep learning to detection of angle of arrival in antennas, in arrays of antennas, and other antenna array processing. And so, for example, we can also apply it to signal processing, to any kinds of signal processing, mainly kernel learning. We can apply it to physics. For example, another prominent line of work is to apply deep learning in order to accelerate the processes in a particle accelerator, in order to produce a much faster computations, estimations, and adjustments of the particle accelerators. We can also talk about physics-informed deep learning that has been used in electromagnetics, and so on. There are a lot of applications that are novel, that are not necessarily tied to images.
Yeah. Anything you want to add, Ramiro, before we go on to the next question? What other applications besides image processing?
Yeah, what I want to open it up a little bit and say, Manel, all these techniques were developed early 80s and the 90s, and we're now beginning to use that. Why do you think is that? Is this because computation has become cheaper? Is it because computers have become more powerful? And just because of that, do you think this is going to really take off and be a popular tool for everybody to use?
Oh, by the way, thank you for your question, Professor Badula. Thank you for your question, Professor Jordan. So that's a very interesting one too. Of course, we have seen a growth of the usage of machine learning due to the advancements in supercomputation and also the advances in parallel computers, right? So now GPUs, or graphical processing units, they're very popular. Anyone can have one at home, and then we are starting to see how the tensor processing units, they have been developed in order to deal with CNNs. And so this accelerated or they boosted the usage of machine learning. But this alone is not sufficient. First, during the first part of the early years of 21st century, a lot more theoretical developments related to deep learning were introduced, mainly by Hinton and co-workers. And so now we know much better how to train highly complex neural networks. So even if this was introduced in the 80s, a lot of theoretical advances have been achieved during the first part of 21st century. And also, we have a lot of new software technologies and programming languages. For example, we have Python, and we have a lot of libraries that are very well developed and stable, and they are able to deal with parallel computation in a transparent and seamless way for the user. And all this together is what have actually boosted machine learning.
So that actually leads to the next question, which you already partially answered, is what are some of the software library tools that are more commonly used for machine learning? And because we know that MATLAB is used a lot, but are there other softwares that people use? You mentioned Python. Can you just talk a little bit about the types of tools on which people should become proficient in order to be able to do work on machine learning?
Yes, well, let's see. There are a lot of different tools for machine learning, but I personally do not recommend the usage of MATLAB for many of the applications. First, because you need a license that is very expensive, and there are tools out there that are for free, right? So, and I'm talking specifically about Python. And in Python, you have a set of libraries which is called TensorFlow. And TensorFlow is a very powerful tool that allows to program parallel structures, specifically deep neural networks, in a very easy way. So the experience for the practitioner is much better than if we use just Python alone. But I particularly recommend the use of PyTorch, which is another set of libraries. All of them, they are accessible for free, and PyTorch is much better for the user to learn and to program easily deep learning structures. And also they can be used for professional development of neural networks.
Okay. Another question, most of us use these on computer. There's a chat bot. Somebody, so the machine is chatting away with you automatically based on questions. How does that work? How does machine learning in the dialogue flow for chatbots? Is that machine learning, or how does that? What's involved in that?
Well, actually, the way in which chatbots work is not actually public, not that I know, right? But I could think of two different sets of technologies. The one that is more prominent from a research point of view is related to recurrent neural networks. So recurrent neural networks, they can input a pattern, for example, a question, and then output an answer. But these neural networks, they need to learn from samples, and these samples, they can only be taken from questions already answered. And the other technology, more easier to implement, is simply to have a database with questions and answers. Then the machine, what it does is to process the question, and then using given metrics, go and provide the answer to the closest question. Mm-hmm. And we have sophisticated ways to do that. But this is all I can say about that. I don't really know this technology.
Thank you. Thank you very much. That was very insightful. Question here is about the percentage of training and testing during deep learning. What is the percentage of training and testing of data? Does the question make sense to you?
This, of course, yes. This is a very interesting question. Many students ask me about that, and then I have two answers: the short and the long. They laugh a lot about that, but I'm serious about that. So the first answer would be, I don't know. And the long question is, well, it heavily depends on your problem, and it will also depend on the structure that you are using. So the data that you have, it is what it is. If you have a problem which you have 100 data, this is what you have. If you have 1 million data, then you won't have a problem. You use as many data as you want for training, the rest for test, right? So if you have many data, there's no problem. But what if you don't have a lot of data? Then what we can do is to train the machine with an increasing number of data and use the rest for test. Then you will see that the learning curve or the performance of the machine increases to a point. And when you arrive to this point, you know that you don't need more data for the training. And then you can use the rest for test. So sometimes it's important to measure this learning curve or learning curve. So start with just a few data and go increasing, and then check what is the performance of the data.
Okay.
There is a lot of heuristics in that topic.
Okay, next question. Is there any common or frequently used machine learning algorithm available to prevent overfitting?
Machine learning algorithm to prevent overfitting? Actually, yes, it makes all the sense. That's another interesting question. I talk here a lot about complexity, right? And complexity is what actually produces overfitting. And in order to prevent it, we have techniques that are called regularization techniques. In kernel learning, regularization techniques are rather explicit, and we have super vector machines. Super vector machines, they use a parameter which is usually called C parameter, and tweaking this parameter, we can control the complexity of the capacity of the machine in order to minimize the overfitting. If we use Gaussian processes, for example, this parameter doesn't exist and the machine is self-regulated. If we use deep learning, then we have explicit regularization techniques that basically consists of minimizing a cost function, for example, the error, and at the same time minimizing the norm of the weights, or a measure of the norm of the weights. And this is a technique called regularization. And then the interested attendant has to take a look to Tikhonov regularization methodologies, Tikhonov. And this is what it contains, all the theory about it.
Okay, a question from Samuel Mukasa is more of the ethical side. How do you and your students view and react to potential abuse of facial recognition technologies by authoritarian dictatorial regimes?
Wow. So
More of political.
This is something that has to be taken from a sociology point of view. And actually, I started work with two experts in this topic, but unfortunately, they moved to another university, so we could not keep going with the work. This is a question that actually I cannot answer, right? What I always say is that if you make knives, these knives, they can be used for saving lives in a surgery room or for killing people, right? The humankind has to evolve from this ethical point of view, but it's not up to us. It's up to the society in general to establish the ethical limits in everything, and in particular in this topic.
Okay, this question has to do with supervised and unsupervised learning. It says, okay, whether unsupervised learning can be used only for classifying the data.
No, let's see. Unsupervised learning can be used in many ways, and one interesting reference is a tutorial on self-supervised learning. Just look for a survey on self-supervised learning, and that paper gives you a wide answer. But non-supervised learning, it can be used for many other things. For example, this application that we saw here, this is non-supervised, right? So we only present the machine the images to which images with a damaged or removed part, and the image, the whole image itself. This is non-supervised, and this is also non-supervised, right? And here we don't perform a classification, but rather than that, a regression, right? There are many other applications of non-supervised learning. It's a very important, prominent area of research.
Okay, question regarding difference between machine learning and artificial intelligence. How are they connected?
Well, machine learning is just a part of artificial intelligence. Artificial intelligence, it contains many more technologies, among them, for example, data analytics, data visualization, right? So if you think of a machine, artificial intelligence is what provides the machine with the capacity to take decisions, to evolve by itself, right? And machine learning is the part of artificial learning that allows the machine to extract the knowledge needed for these decisions. But there are many more things around it that are not machine learning, but they can be considered artificial intelligence.
What kind of basic courses, background courses does a student have to have in order to start doing some research in machine learning?
Well, there are many out there, but what I'm teaching for my students to start doing research is first an introduction to statistical learning theory. This is kernel learning or shallow learning. Then I recommend everyone to have a class in deep learning too. Plus, for more advanced students, probabilistic learning, but kernel learning and deep learning first.
Mm-hmm. And those are mostly from in the Department of Computer Science, or which
well, yeah, computer science and computer engineering. I always work in a computer department, engineering department. I also advise the students to have a solid background in algebra and calculus and basics of probability theory. This is very important.
Mm-hmm. So, so in undergraduate area, if somebody wants to get into artificial intelligence, it can be any discipline, right? It can be mechanical, it can be other disciplines that can get into artificial intelligence, right?
Yes, yes. Artificial intelligence in general and machine learning in particular, they are void technologies. Void. We need to find problems to solve. And these problems to solve, they are in mechanical engineering, in physics, in math, in electrical engineering, in medicine, etc. So basically, I prefer that people study some real engineering or science, and then they have background in machine learning, not all the way around.
That makes sense. So yeah, we talked about research collaborations, and Ramiro also mentioned that. Can you and Ramiro maybe talk a little bit about what kinds of research collaborations can you encourage between what's happening at your university, maybe other universities? How can we have some global collaborations in research in this general area, and how does it connect to peace engineering? Ramiro, you want to jump in, or or even Manel, either one of you both?
I think Ramiro is the key person here to talk about this. Please, Ramiro.
Ramiro, you're unmuted, so you can talk.
Yes. Since we launched the new definition of peace engineering and the first global peace engineering conference that we hosted, it was at IFEES GDC in 2018, people have embraced it, and we have started coming up with data metrics and data on how to measure positive and negative interactions. We can quantify, which with this data being used now with AI, machine learning, we can predict whether we can prevent conflict or not. So this is a real application of peace engineering. We are working with many institutions and also the national labs to come up with like a weather prediction environment. Weather prediction is very hard, just to let you know. It's very difficult to predict what's going to happen. So this is the same setup that we're trying to come up with maps that we can predict and avoid conflict. How can we improve better relations? Today, we can measure in real time anger, trust, empathy. So we can use now these, and we can quantify, and we can look at positive peace and negative peace. So this is a big area that's opening up globally, especially now that we are under stress because of COVID. Every model is being reimagined, re-engineered. The health system, the energy system, the telecommunications, the finances. So all of a sudden it just opened up, and we need collaboration so we can start working together. And Sam sent something very important, and this is something of peace engineering. Any technology can be weaponized, any. So we just want to make sure that we don't do that. Thank you.
Thank you, Ramiro, and thank you so much, Manel. That was such a fascinating, very informative and educational webinar that you gave. And as you can see from the questions, 200 plus people have engaged. And thank you very much. And everybody, stay healthy, stay safe, and stay happy. Good night, good morning, good evening, everybody. Take care.
Thank you very much. It was an honor to be part of it.